going to look over independent events in probability, and we're going to focus on Sick Kids Lotto. They sent us a thing in the newspaper, or sorry, in the mail, and we quickly took a look at all the possible prizes. Okay, so these are everything you can win. Okay, so you can read them all out, and we tallied them up, and this is the total. Plus, there's the idea of a 50-50 draw. We're going to keep this nice round number. Okay, we'll keep the 50-50 draw kind of out of the idea. Okay, so we're going to talk about what an independent event would be. Okay, and we can use these concepts. So, like we said, there were, I'm going to write it so we can fit it on one page, 55,310 total prizes. Okay, so the other thing we kind of need to find out is how many total tickets there are going to be. Okay, now we'd have to watch or go over the idea of odds after, but I'm just going to tell you that according to the odds in this, we'd have to multiply by the number of 3 to figure out how many total tickets they're going to have. And this total will tell us what your probability or what your ticket's chance is. So we take that number we had before and multiply it by 3, 15, so 150, 930. 150, 930, okay? This is a general estimate of how many tickets they sell, okay, in order for their odds to be true. So, here's our first question. All of these are the early bird stuff, but we assume they're all included in the number of prizes with our odds. So, if we were to do independent events, we're going to say independent event is where you take the probability of event A, okay, and you would multiply it by the probability of event B happening, and that would be the probability of both events. Okay, so that would be we'll call it probability of C is the probability of A times the probability of B, and usually they would write it as probability of A and B for independent events. They write something like this: A and B. Is that how they write in your book? Something like that? Yeah. Okay. So we want to know the probability of 2 events happening. Okay, and we're going to go on the assumption they're independent, and we're going to talk about how that's not quite true in this case, and then we'll do a different one on dependent events. But let's say we want to know what's the probability that you win the VIP draw, okay, and you win the grand prize draw. Because they're one of them, we're going to go on the assumption that these are the 2 biggest. Okay, these are the 2 biggest ideas here. So the probability of this event happening, that you win both. Well, there's a 1 in, how many tickets are sold, did we say? 50,000, yeah. So winning the VIP draw, that's going to be our probability of A, okay? Probability of A is going to be equal to 1 in 150,930, okay? And the probability of event B is going to be, we said that'd be grand prize, will be identical to the probability of A. Now, the only thing is, these need to be independent events, okay? So what that means is, we go on the assumption that we buy 1 ticket, we say, okay? So I only buy 1 ticket. In order for me to win both prizes, when they draw me in the early draw, that VIP draw, I go ahead and I win this, what do they have to do with my ticket in order to keep this same probability for it to be independent? Do you know? That ticket has to be re-put into the pool, okay? So you have your, sort of my jar with billions of tickets, okay? They draw 1 ticket out, okay? For it to be an independent, okay, that means the probability of the first one doesn't affect the second, they actually have to put my ticket back into the pot, which means my 1 ticket, if they're doing that, could potentially win a prize, could win every prize because they keep putting it back in. Probability of this idea happening is so small, it's ridiculous. But that would make them independent events. Okay? If they draw my 1 ticket out of our wonderful pot of stuff and they don't replace it, well, now there's no longer this many tickets. There's 1 less. Okay? And that would be a dependent event. And that would change the probability of event B happening. Okay? So probability of individual events, we have them as our fractions. Probability of A and B, okay, is obviously the 1 over 150, 930 times 1 over 150, 930 ridiculous numbers. Okay, I'm just going to tell you, when we multiply fractions, we're looking at 1 over, and because these values are the same, squared. I'm just going to put it as a value squared. I don't know if my calculator will even calculate this. Let's find out. 1 divided by bracket 150,930 to the power of 2 is equal to ridiculous. There are 10 decimal places with the 0 in front of that 4 as a percentage. Okay, so not happening. That's pretty much how you can see that idea of that not happening. Okay, but let's do another one independent. Let's say we want to know the probability of you winning, and these are the minor. I should have wrote the word minor here. The minor early bird draw. That's 5,850, and getting in the final minor draws. And again, we're assuming they're independent events. So the first one had 5,850. Okay, so there's 5,850 of those tickets out of the total 930 tickets. And our other probability, so that was our probability of A. And our other probability is the final minor draws. Well, there's 44,425 out of the 150,930. Okay, so the probability of those two events happening is a little different. Okay, and I've written it this way because the idea is this is how many chances you get out of the total number of tickets. Okay, so 5,850 of the total 150,930 tickets will be winners of the early bird draw. Let's assume all these tickets are in place for the early bird draw. And then 44,425 tickets are out of the total of, again, 150,930. So same concept. For it to be independent, okay, we have to say that when they draw this ticket, whatever the number is, it then goes back into the pot for them to be independent events. Okay, and we know that that is very unlikely that idea is happening. So again, to calculate this, we multiply top by top, bottom by the bottom. Let's see if I can. 5,850 times 44,425. I'm sure it's going to give us a big number. Ooh. And instead of writing that out, remember the denominator will be the same. It's 150,930 squared. I'm going to take that value and divide it by the 150. Are you okay with the idea here of squaring these things?
Yeah.
Yeah? I'm squaring it because I just don't want to multiply and have to write that huge, huge number. So when we divide them, this is giving us the percentage. This is the, well, almost a percentage. We technically have to multiply by 100. But the idea of that idea of possibly happening, you have 0.011, okay? And that's a decimal value. We'll round it 0.01 as a decimal, okay? And technically it rounds down, so we'll say approximately, which means your percent, where is it? Here we go. We technically take this value and you multiply by 100 to find a percentage value. 1.14, so approximately a 1.14% chance of winning one of those little prizes. Okay? Well, of winning both of those prizes, or one in both of those. Again, pretty unlikely it's going to happen. Okay? But that's the idea of independent, where we take that ticket out and we put it back in. The first event did not affect the second event.